Welcome back. Let's practice finding directional derivatives. Alright, so here's our first example. We want to find the directional derivative at the point 1, -2 in the direction of the vector that makes an angle of theta equals pi divided by 4 with the x-axis. And we've been given this multivariable function, f of xy is equal to x squared plus y squared. Alright, so in order to find a directional derivative, you need to know the formula. It looks like this. The derivative in the direction of a unit vector u for a multivariable function, f of xy is equal to the partial derivative of f with respect to x multiplied by the x component of the unit vector u sub 1 plus the partial derivative of f with respect to y times the y component of the unit vector u sub 2. Okay, and so the first thing I'm going to do here is find these two partial derivatives. Let's find both fx and fy for this multivariable function, starting with fx. Looking at our function here, the first term is entirely in terms of x, so its derivative is pretty simple. Just use the power rule for derivatives, and the derivative of x squared is 2x. And then for the second term, y squared would just be a constant because we're taking a partial with respect to x, so we're treating y as a constant, which means y squared is a constant whose derivative is 0. So we just get 2x for fx, but then for fy, or the partial derivative with respect to y, now we're treating x as a constant. So the first term here, x squared, would be a constant whose derivative is 0, and then y squared, you do want to differentiate that using the power rule, and you will get 2y. Okay, and so 2y is fy. And so now we have the first partial derivatives of our multivariable function, which means the only thing we don't have here that we need in order to calculate the directional derivative are the components of the unit vector that is describing the direction in which we want to find this derivative. And so how do we find that? Because as you might have noticed, we were not explicitly given a unit vector here. Instead, what we've been told is that the directional derivative we want to find should be in the direction of the vector that makes an angle of theta equals pi divided by 4 with the x-axis. We can use that angle that we've been given to find a unit vector. We learned this earlier in Calculus 3, that a unit vector, which is a vector with a magnitude of 1, can be defined like this. You'll have cosine theta times I plus sine theta times j, where theta is the angle that the vector makes with the x-axis, the exact angle that we've been given here. So, in this case, our unit vector would be equal to cosine of pi divided by 4, I, plus sine of pi divided by 4, j. Okay, our angle of theta is pi divided by 4. That is the angle that the vector makes with the x-axis, specifically the vector that has the direction for which we want to find this directional derivative, and so we can use that angle to find our unit vector. And so simplifying here, cosine of pi divided by 4 is the square root of 2 divided by 2, as is sine of pi divided by 4. So altogether, we get that the unit vector is equal to the square root of 2 divided by 2 times I plus the square root of 2 divided by 2 times j. Alright, and so this is our unit vector for this directional derivative. The x component is the square root of 2 divided by 2, and the y component is the square root of 2 divided by 2. Those are our values of u1 and u2, which means we now have everything we need to calculate this directional derivative. So let's set it up. This will be equal to fx, which we found is 2x, multiplied by u1, the x component of the unit vector. So we have the square root of 2 divided by 2, and then we have plus fy, which is 2y, and then we're multiplying by u2, the y component of the unit vector, which is the square root of 2 divided by 2. Okay, again, u1 equals the square root of 2 divided by 2, and u2 also equals the square root of 2 divided by 2. In case that wasn't clear before, we get those values directly from those two components. Alright, but now simplifying, these 2's will cancel out, and so will these 2's, just leaving us with the directional derivative of the square root of 2 times x plus the square root of 2 times y. Or if you wanted to, you could pull out that common factor of the square root of 2 and just have the square root of 2 times x plus y. Okay, but either way, that would represent the directional derivative, at least in terms of x and y. Really what this is an equation that will give you the slope of the tangent line at any point on this surface, but only in the direction of this unit vector. that makes this angle with the x-axis. Okay, so we have an expression that will give us the value of the slope at any point in that direction. But in this problem, we do want to find a specific slope, which is the directional derivative at the point 1, negative 2. And so all we have to do to find that is plug in x equals 1 and y equals negative 2 into our directional derivative. So let's do that here. We will have that the derivative in the direction of the unit vector u for f of 1, negative 2, right? We're letting x be 1 and y be negative 2, and that will be equal to the square root of 2 times x, which is 1, plus the square root of 2 times y, which is negative 2, or maybe an easier way of looking at it, if we rewrite the directional derivative here and pull out that common factor as I said, you would have the square root of 2 times the quantity of x plus y. Then you could write it like this. It might just be a little bit easier to calculate. You have 1 plus negative 2 times the square root of 2, and 1 plus negative 2 is negative 1, and negative 1 times the square root of 2 gives you the negative square root of 2. All right, and so that would be the value of the slope or the directional derivative at the point 1, negative 2 on this surface in the direction of this unit vector. Okay, let's take a look at another example. Next up, we want to find the directional derivative at the point 3, 0 in the direction of the vector that makes an angle of theta equals negative pi divided by 6 with the x-axis. And our multivariable function this time around is f of xy is equal to y divided by x plus y. All right, so this example is very much like the last one. It's just that we're given a different function, a different point, and a different angle. So our solution process will be the same. We're still going to use the same formula. The derivative in the direction of a unit vector u for our multivariable function f of xy is equal to the partial derivative with respect to x times the x component of the unit vector plus the partial derivative with respect to y multiplied by the y component of the unit vector. Okay, and so once again, let's begin by finding the two partial derivatives, beginning with fx. What would that be equal to? Well, looking at our function here, x is in the denominator of this rational expression, but it's not in the numerator, so we don't necessarily have to use the quotient rule here. What we could do is rewrite this function like this. We could have y times that quantity of x plus y to the power of negative 1. All right, move that quantity to the numerator by making its power negative, and now we have something that's a little bit easier to take the derivative of. Because y, with respect to x, is a constant, so this is just a constant multiplied by this quantity. So really you only have to worry about taking the derivative of this part. And we will have to use the chain rule here, because you have an outside function of that quantity to the power of negative 1, and an inside function of x plus y. All right, so start by taking the derivative of the outside. I'll use the power rule, multiply that negative 1 down, and you get negative y times x plus y to the power of negative 2, right? Subtract 1 from that exponent. Then you want to multiply by the derivative of the inside function, but that would just be 1, right? The derivative of x is 1, and y is just a constant with respect to x, so its derivative is 0. So you'd be multiplying by 1 here, but that doesn't really change anything, so I'm not going to worry about that. But then we can rewrite fx to look a little bit nicer, move this quantity to the denominator, and you get negative y divided by x plus y squared. Okay, so that's fx. Now let's find fy, the partial derivative with respect to y, and in this case we will have to use the quotient rule because y is in the numerator and the denominator of this function. So let's use the quotient rule here. Start by taking the bottom function. So we have x plus y times the derivative of the top, and the derivative of y with respect to y is just 1. Then we will subtract that top function times the derivative of the bottom, and the derivative of x with respect to y is 0. X would just be a constant, and the derivative of y is 1. So you have minus y times 1, and all of this is divided by that denominator x plus y squared. All right, now in the numerator here, x plus y times 1 is just x plus y, and y times 1 is just y. So if I erase these parentheses and that multiplication of 1, as well as this right here, now you can see how to easily simplify this. This y and this negative y will cancel out, just giving us that fy is equal to x divided by x plus y squared. All right, and so now we have both fx and fy, the first partial derivatives of our multivariable function, which we can use to find the directional derivative. Okay, so that takes care of that, but we still need the components of our unit vector. Remember that when you're given the angle that the vector makes with the x-axis, you can set up a unit vector using this formula. That unit vector is equal to cosine theta times I plus sine theta times j. So in this case, we'll get that the unit vector is equal to cosine of negative pi divided by 6, right? That's our angle of theta that we've been given. That's multiplied by I, and then we have plus sine of negative pi divided by 6 times j. And so simplifying, cosine of negative pi divided by 6 is a square root of 3 divided by 2, and so that's the x component. And then for the y component, sine of negative pi divided by 6 is negative 1/2. So instead of plus, we will have minus 1/2 times j. Okay, so the x component, u1, is a square root of 3 divided by 2, and the y component, u2, is negative 1/2. So now we have everything we need to set up this directional derivative. So let's do it. This will be equal to fx, which is negative y, divided by x plus y squared, times u1. So we're multiplying by the square root of 3 divided by 2, plus fy, which is x divided by x plus y squared, and that's multiplied by negative 1/2. All right, and so then simplifying this, notice that these two terms will have a common denominator, right? Both of them will have x plus y quantity squared times 2. We have that right here and right here. So we can combine the numerators and get one expression here of the negative square root of 3 times y minus x divided by 2 times x plus y squared. All right, I multiplied the square root of 3 by negative y, so we have the negative square root of 3 times y, and then when you multiply negative 1/2 by this, you want to attach that negative to x. All right, so that's why we have minus x. But then we have a common denominator, so both of those two terms are divided by 2 times the quantity of x plus y squared. Okay, and if you wanted to, you could pull out a negative from these two terms. So if you really want to make this look nice, you could have negative x plus the square root of 3 times y divided by 2 times x plus y squared. Okay, I also just reordered those two terms because it's more common to write the x term before the y term, but really it doesn't matter. The order of addition does not matter. Okay, but that right there would be the directional derivative, at least in terms of x and y. But remember that we do want to find a specific directional derivative here at the point 3, 0. So let's plug in 3 and 0 for x and y. If we do that, we will get that the derivative in the direction of u for f of 3, 0 is equal to negative 3 plus the square root of 3 times 0 divided by 2 times 3 plus 0 squared. All right, we plugged in 3 for each of those x's and plugged in 0 for each of those y's. And so simplifying, the square root of 3 times 0 is 0, so you just have 3 times negative 1. So we get negative 3 in the numerator, and then in the denominator, 3 plus 0 is 3, 3 squared is 9, 9 times 2 is 18. So we have negative 3 divided by 18, which reduces to negative 1/6. And that right there would be the directional derivative, or the slope, at this point on this surface in the direction of the vector that makes an angle of theta equals negative pi divided by 6 with the x-axis. This unit vector right here. Okay, let's take a look at a slightly different example. For this example, we want to find the directional derivative at the point 2, 3 in the direction of vector v. And we're given f of xy is equal to 3x minus 4xy plus 9y, and vector v is equal to 3/5 I plus 4/5 j. So we're still trying to find a directional derivative here in this example, but the information that we've been given to do so is a little bit different. This time around, we are not given an angle that the vector makes with the x-axis. And so the way we get the components of our unit vector will be a little bit different. Although it's not too complicated, as you'll see in just a second. But before we do anything, remember that this is the formula that we're going to use, the derivative in the direction of a unit vector u for this multivariable function, f of xy is equal to fx times u1 plus fy times u2. Okay, the partial derivatives with respect to x and y, and then the x and y components of the unit vector. And let's start once again by finding the partial derivatives. And so if we start with fx, what will that be equal to? For the first term, the derivative of 3x is 3, so we have 3. And then for the second term, negative 4xy, the derivative of that would just be negative 4y, because we're treating y as a constant, and x is to the first power, so its derivative would be 1, and 1 multiplied by negative 4y is negative 4y. Okay, so we have 3 minus 4y, and that will be it, because for this last term, 9y with respect to x is a constant, so its derivative is 0. So that's fx, but then for fy, the first term would be a constant, there's no y's there, so 3x is a constant whose derivative is 0, and then for negative 4xy, the derivative of y to the first power is 1, and 1 times negative 4x is negative 4x, and then the derivative of 9y with respect to y is positive 9. Okay, and if you prefer to reorder the terms, you could write it as 9 minus 4x, and it looks a little bit nicer, but it doesn't really matter. But that is how I'm going to use it here. And so now we have the partial derivatives. Now let's focus on the unit vector. How do we find these two components, u1 and u2? Well, you might be tempted to just grab them straight from the vector that we've been given, but you have to be careful. You want to make sure that the vector that you've been given is a unit vector, because this formula for a directional derivative is assuming that u1 and u2 are the components of a unit vector, a vector with a magnitude of 1. We are not specifically told that that is the case for this vector here. We're just given a vector v with these components. So what we want to do is check to see if its magnitude really is 1, which is what it should be if it's a unit vector. And if it's not, then we'll just make the vector a unit vector, because you can find a unit vector by dividing a vector by its own magnitude. All right, so let's check it here. Let's see what the magnitude of vector v is. To find that, we'll take the square root of the sum of the components squared. So we'll have 3/5 squared plus 4/5 squared. And so simplifying, 3 squared is 9, 5 squared is 25. So we have the square root of 9 divided by 25 plus 4 squared, which is 16. 5 squared is 25. So we have 16 divided by 25. And then these two terms have a common denominator, so you can add the numerators. 9 plus 16 is 25. So we get the square root of 25 divided by 25, which is 1. So you get the square root of 1, which is 1. So the magnitude of vector v here is 1, which is good. That's what we want. That means that this vector is a unit vector. We don't have to change anything here. We can actually use these components as our values of u1 and u2 in this formula. So that worked out pretty nicely in this case, but that will not always happen. The vector that you've been given will not always be a unit vector. Okay, so if we had found that this magnitude was not 1, meaning it was not a unit vector, what we could then do is just divide the vector by the magnitude that we found. Because remember, a unit vector is equal to a vector divided by its magnitude. Okay, this is a formula that we learned earlier in Calculus 3. But we didn't have to use that here. We already were given a unit vector. So now let's just find our directional derivative, because we have everything that we need. Our vector v is also the unit vector u, where u1, the x component, is 3/5, and u2, the y component, is 4/5. All right, so our directional derivative will be equal to fx, which is 3 minus 4y times u1, so we're multiplying by 3/5, and then we'll add that to fy, which is 9 minus 4x, and then you want to multiply that by u2, which is 4/5. Okay, and then simplifying, let's distribute 3/5 through this quantity and 4/5 through this quantity. If you do that, you'll get 9/5 minus 12/5 times y plus 36/5 minus 16/5 x. And then we can combine these two constant terms. 9/5 plus 36/5 would be 45/5, right? You get 45/5, but 45 divided by 5 is 9. So I'm just going to write down 9. So we have 9, and then I'll write down the x term and the y term. We have 9 minus 16 divided by 5, x minus 12 divided by 5 times y. And that right there is the directional derivative in terms of x and y. It is the equation that will give us the slope of the tangent line at any point on this surface in the direction of this vector. But now we want to find the specific slope or the specific directional derivative at the point 2, 3. So let's plug in 2 and 3 for x and y in this expression. We will find that the derivative in the direction of u for f of 2, 3 is equal to 9 minus 16 fifths times 2, that's the value of x, minus 12 fifths times 3, that's the value of y. All right, so 2 times 16 is 32, 3 times 12 is 36. So what we get here is 9 minus 32 fifths minus 36 fifths. So we have 9 minus 68 fifths, which doesn't look like it's going to be a very nice number. But 9 in terms of fifths, if we do that work on the side here, is 45 fifths, because 45 divided by 5 is 9. And so 45 fifths minus 68 fifths, that will give you negative 23 fifths. And so that will be the final answer. Okay, so I'm just going to erase this here. We will get negative 23 fifths as the value of the slope. Okay, that would be the directional derivative at this point 2, 3 on this surface in the direction of vector v, which is a unit vector. Hey, real quick, before we take a look at the next example, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me in the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. Next up, we want to find the directional derivative at the point 0, 0 in the direction of vector v, and we're given f of xy is equal to e to the power of negative x squared plus y squared, and then vector v is equal to 2i plus 3j. All right, so this is just like our previous example. We're not given an angle that the vector makes with the x-axis, so instead what we have to do here is check to see if this vector that we've been given is a unit vector, and if it's not, make it into a unit vector that we can then use to find the directional derivative. Okay, so we will do that, but first, let's write down our formula. The derivative in the direction of a unit vector u for the multivariable function f of xy is equal to fx times u1 plus fy times u2. All right, so let's start by finding the partial derivatives. Let's find fx. Looking at our multivariable function here, x is in the power of e, so we do need to differentiate that expression. Remember that the derivative of e to a power is just itself, but then multiplied by the derivative of that power. So fx will be equal to e to the power of negative x squared plus y squared, and then you want to multiply by the derivative of that exponent. And with respect to x, y squared is a constant, its derivative is 0, but then x squared, its derivative is 2x, but don't forget about that negative, so we get negative 2x. All right, and then for fy, you'll get a very similar derivative. You'll still have e to the power of negative x squared plus y squared, but then the derivative of that exponent with respect to y will be negative 2y. Right? X squared is a constant, its derivative is 0. The derivative of y squared with respect to y is 2y, but don't forget about this negative, so you get negative 2y. Okay, so those are the partial derivatives. Now let's check our vector, because we do need u1 and u2, the x and y components of the unit vector, which has the direction for our directional derivative, but we can't assume that the vector that we've been given is a unit vector, so we can't just say that u1 is 2 and u2 is 3. We have to make sure that this vector has a magnitude of 1. So let's see if that's the case here. Let's take the magnitude of vector v. That will be equal to the square root of 2 squared plus 3 squared, right? The sum of the components squared. And so 2 squared is 4, 3 squared is 9, resulting in the square root of 4 plus 9, which is the square root of 13. And so that is not 1, right? which means that this is not a unit vector, but we can make it into a unit vector by remembering that a unit vector is equal to a vector divided by its magnitude. All right, so we can just take our vector here, divided by the magnitude that we found, and then we will have a unit vector that we can use to find a directional derivative. So in this case, just divide both 2 and 3 by the square root of 13, and that will be the unit vector. All right, so we have u is equal to 2 divided by the square root of 13 times I plus 3 divided by the square root of 13 times j. So u1 is equal to 2 divided by the square root of 13, and u2 is equal to 3 divided by the square root of 13. Okay, and so now we have everything we need. We just have to put everything together now into this formula. So let's do that here. The directional derivative will be equal to fx, which is negative 2x times e to the power of negative x squared plus y squared, times u1, so we're multiplying by 2 divided by the square root of 13, and then we're adding fy, which will be negative 2y times this exponential function, so I'll write in minus 2y times e to the power of negative x squared plus y squared, and then we will be multiplying by u2, which is 3 divided by the square root of 13. All right, and so to simplify here, we do have a common factor in these two terms of negative 2 times e to the power of negative x squared plus y squared. So I'm going to pull that out, and here's what we'll get. This will be equal to negative 2 times e to the power of negative x squared plus y squared multiplied by x times 2 divided by the square root of 13 plus y times 3 divided by the square root of 13. Okay, but now what we could do here is combine these two terms because they have a common denominator of the square root of 13. So I'm just going to do that right here in this step. We will have 2x plus 3y divided by the square root of 13. Okay, once again, I just pulled out negative 2 times e to the power of negative x squared plus y squared from both of these two terms, so that's on the outside now, just leaving you with x times 2 divided by the square root of 13, which is where we get this 2x right here, and then in this term you're left with y times 3 divided by the square root of 13, which is where we get this 3y right here. And that right there would be the directional derivative in terms of x and y, but we do want to find the specific directional derivative at the point 0, 0. So let's work on that now. That will look like this. The derivative in the direction of u for f of 0, 0 is equal to negative 2 times e to the power of negative 0 squared plus 0 squared, but that would just be 0, right? That whole exponent would just become 0, because we're plugging in 0 for both x and y, and that will be multiplied by 2 times 0 plus 3 times 0 divided by the square root of 13. Okay, and so 2 times 0 is 0, 3 times 0 is 0. So we have 0 divided by the square root of 13, which means we have 0 times negative 2 times e to the power of 0. Doesn't matter what this is, it would just be negative 2, but you're multiplying it by 0, so the whole thing is 0. The slope at that point in the direction of this unit vector is 0. That is the answer to this example. The point 0, 0 on this surface has a slope of 0 in this direction. For our next example, we want to find the directional derivative at point P1 with coordinates of 1, 1 in the direction of point P2 with coordinates of 6, 13. And we're given a multivariable function f of xy is equal to 3x squared times y squared. All right, so this is a little bit different than any of our previous examples. We're still finding a directional derivative, but the information that we're given is a little bit different. We're not told the angle that a vector makes with the x-axis, and we're also not given a vector. We're just told to find the directional derivative at a point in the direction of another point, which seems weird, but it is information that we can work with. Because whenever we're finding a directional derivative, we always need a unit vector. And if you remember back to earlier in Calculus 3, we can always find a vector if we are given 2 points, right? We can find a vector that connects point P1 to point P2, which would have the direction we're looking for. So what we'll do here is find a vector between these 2 points and then make it a unit vector, because most likely it's not going to be a unit vector at first. We will have to find its magnitude and then divide that vector by it. Okay, so we will do that here. But before we get started, I want to write down the formula the derivative in the direction of a unit vector u for our multivariable function f of xy will be equal to fx times u1 plus fy times u2. Okay, that will never change. This is always the same for these examples. And so I'll start by finding the partial derivatives. We'll worry about the vector later. And so beginning with fx, what would be the partial derivative with respect to x of this function? Well, y squared would be a constant, so just ignore that and take the derivative of x squared. Use the power rule, multiply that 2 down, subtract 1 from the exponent, and you'll find that fx is equal to 6x to the first power times y squared. And then for fy, we now treat x as a constant, so leave x squared alone, and just take the derivative of y squared using the power rule. So multiply the 2 down, subtract 1 from the exponent, and you get 6x squared times y to the first power. Okay, so that takes care of the partial derivatives. Now let's focus on the vector. And we'll start by just finding a vector v that is not necessarily a unit vector. What we'll do is take the x-coordinate of the second point and subtract the x-coordinate of the first point, and that will make up the x component of the vector. And then we'll do the same thing for the y component. We'll take this y-coordinate for point 2 and subtract the y-coordinate for point 1. Okay, this is how we find a vector between 2 points. So we'll have 6 minus 1 times I plus 13 minus 1 times j. And so simplifying, we get a vector with an x component of 5 and a y component of 12. Okay, now just by looking at that, it's pretty clear that this is not going to be a unit vector, but whether you can tell that or not, it doesn't matter, because you still have to calculate the magnitude of this vector to be able to turn it into a unit vector. So calculating the magnitude here serves two purposes. We can check to see if the magnitude is 1, and then if it's not, we can just use that magnitude to help us find the unit vector. Okay, so take the square root of the sum of the components squared. We'll have 5 squared plus 12 squared, and 5 squared is 25, 12 squared is 144, so this is equal to the square root of 25 plus 144, which is 169, and the square root of 169 is 13. So we do get a nice value for the magnitude, but it's not 1. So the vector that we have here, the vector that connects these 2 points, giving us the direction for our directional derivative, it's not a unit vector, but we can make it into a unit vector by dividing it by its magnitude. All right, the unit vector will be equal to vector v divided by its magnitude. So we will get that the unit vector is equal to the x component of 5 divided by 13, the magnitude. So we have 5/13 I plus the y component 12 divided by the magnitude of 13. So we have 12/13 times j. So u1 is 5/13 and u2 is 12/13. Okay, so now we have everything we need to set up this directional derivative. So let's do it. We'll have that this is equal to fx, which is 6x y squared, times u1, which is 5/13, plus fy, which is 6x squared y, times u2, which is 12/13. And then simplifying, this will be equal to 30/13 times xy squared plus 72 divided by 13 x squared y. And that's about it. There's really nothing else we can do to make this look a whole lot nicer. So I'm just going to leave it in that form. That would be the directional derivative in terms of x and y. But now let's find the specific directional derivative at this point right here, right? We want to find the directional derivative at point P1 with coordinates of 1, 1 in the direction of this other point. So we're not going to evaluate this directional derivative at 6/13. That's just helping us get the direction for the derivative. We really want to find the slope or the derivative at 1, 1. So those are the values that we will plug in to our directional derivative. All right, so let's do that here. We will have the derivative in the direction of u for f of 1, 1 is equal to 30 divided by 13 times 1 squared plus 72 divided by 13 times 1 squared times 1. All right, both x and y become 1, which makes this a pretty easy calculation. We will just get 30/13 plus 72/13, which will be 102/13. All right, that would be the slope or the directional derivative at point P1 with coordinates of 1, 1 on this surface in the direction of this unit vector, or really in the direction from this point to this point. Okay, let's take a look at one more example for this video. All right, so for our final example, we want to find the directional derivative at point P1 with coordinates of pi 0 in the direction of point P2 with coordinates of pi divided by 2 pi. And we're given the multivariable function f of xy is equal to sine of 2x times cosine y. All right, so this is just like the previous example. We want to find a directional derivative, but what we are given are 2 points. We know we want to find the derivative at a specific point, but in the direction of another point. So we will use the same process of finding a vector between these 2 points and then turning that vector into a unit vector that we can then use to find the directional derivative. Okay, so one more time, our formula is that the derivative in the direction of a unit vector u for our multivariable function f of xy is equal to fx times u1 plus fy times u2. Okay, so let's start with the partial derivatives. Let's find fx and then fy. For fx, we need to take the derivative of sine of 2x, but then cosine y is just a constant with respect to x. So that's essentially just the coefficient or number being multiplied by sine of 2x. So just take the derivative of sine here. The derivative of sine is cosine, so you'll have cosine of 2x, but then don't forget to multiply that by the derivative of the inside function, which the derivative of 2x would be 2. So really, let me rewrite this. We would have 2 times cosine of 2x times cosine y. All right, so that would be fx, or the partial derivative with respect to x. But then what about fy, the partial derivative with respect to y? Well, in this case, sine of 2x would just be a constant, or the coefficient of cosine y, because we're treating x as a constant now. So just take the derivative of cosine y. And the derivative of cosine is negative sine, so I'll put the negative out front, and we'll have negative sine of 2x times sine of y. Okay, and so those are the partial derivatives. Now let's find our unit vector, and we have to start by finding a vector using these 2 points. So we'll do the same thing we did in the previous example. For the x component, we'll take the x-coordinate of the second point minus the x-coordinate of the first point, and then for the y component, we'll take the y-coordinate of the second point minus the y-coordinate of the first point. So vector v will be equal to pi divided by 2 minus pi times I plus pi minus 0 times j. Okay, now pi divided by 2 minus pi will be negative pi divided by 2. So this is equal to negative pi divided by 2i. And then pi minus 0 is just pi. So we have plus pi times j. Okay, so that's the vector that connects these 2 points. It will be in the direction of this point from this point. And now we want to check to see if it's a unit vector or not. So let's find the magnitude of vector v here. We'll take the square root of the sum of the components squared. And so we have negative pi divided by 2 squared plus pi squared. That will simplify to the square root of pi squared divided by 4 plus pi squared. And you could combine these 2 terms. You can multiply pi squared by a form of 1 of 4 divided by 4. So they would have a common denominator that you could then combine, right? So we'll do times 4 divided by 4. So you would have 4 pi squared divided by 4 plus pi squared divided by 4, which gives you the square root of 5 pi squared divided by 4. And so you can take the square root of pi squared and 4, giving you a final answer that the magnitude is the square root of 5 times pi divided by 2. Okay, so that's the magnitude, which is very clearly not 1. So we don't have a unit vector right here. We need to turn it into a unit vector by dividing these components by the magnitude that we just found. So let's do that here. Remember that a unit vector is equal to a vector divided by its magnitude. So in this case, we will have negative pi divided by 2, which is the x component, divided by this magnitude, which instead of dividing by that fraction, what I'll do is multiply by its reciprocal, which is the same thing. You can do that. So we'll multiply by 2 divided by the square root of 5 pi. Okay, just flip the numerator and denominator and multiply by that fraction, which is the same as dividing by the original fraction. Okay, so that's the x component. And then for the y component, we'll have pi times 2 divided by the square root of 5 pi. We're dividing by the same fraction, so I'm multiplying by the same reciprocal. All right, and so that would be the y component, so multiply it by j. And then, simplifying, these 2's will cancel out, and these pi's will cancel out, and so will these pi's, giving us a unit vector of -1 divided by the square root of 5 times I plus 2 divided by the square root of 5 times j. Okay, and so that will be our unit vector. In this case, u1 is equal to -1 divided by the square root of 5, and u2 is equal to 2 divided by the square root of 5. And so now we have everything we need to find our directional derivative. So let's set it up. We will have that the directional derivative is equal to fx, which is 2 cosine of 2x times cosine y times u1. So we're multiplying by -1 divided by the square root of 5 plus fy, or really it will be minus because fy is negative. So let me rewrite that here. We will have minus sine of 2x times sine y multiplied by u2, which is 2 divided by the square root of 5. All right, and then simplifying, this will be equal to -2 divided by the square root of 5 times cosine of 2x times cosine of y minus 2 divided by the square root of 5 times sine of 2x times sine y. Okay? And that would be the directional derivative in terms of x and y. Notice that you could pull out a common factor of -2 divided by the square root of 5 from both of these two terms, but I'm not going to do that here, just for the sake of time, and it really won't matter when we go to find the specific slope here at this point, because as you'll see, one of these terms will just be 0. And so let me show you that now. Remember that we do want to find the specific directional derivative, the derivative in the direction of u, for f of pi 0. Right, we want to find the directional derivative at this point with coordinates of pi 0, not this point. This point just helps us get the direction, or the unit vector, for that directional derivative, but this is the actual point that we want to find the slope, or the directional derivative at. Okay, so those are the coordinates that we will use. We will plug in pi for x and 0 for y, so this will be equal to -2 divided by the square root of 5 times cosine of 2 pi times cosine of 0 minus 2 divided by the square root of 5 times sine of 2 pi times sine of 0. Now, simplifying, this is pretty nice because sine of 2 pi and sine of 0 are both equal to 0. So anything times 0 is 0. So this whole term is just 0. All right, so you can cross this out. That goes to 0. So you just have to focus on this first term here, and cosine of 2 pi and cosine of 0 are both equal to 1. So we'll just have -2 divided by the square root of 5 times 1, which is just -2 divided by the square root of 5. Okay? And so that right there is the derivative, or the slope, at this point on this surface in the direction of this point, or really in the direction of this unit vector. Okay, and so that's it for this example, and this was also the last example for this video, but if you do want to get some more practice finding directional derivatives, I have another one available on my membership site, so if that's something that interests you, feel free to look into becoming a member. You can find all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.